All right, so let's just revise a bit of what we're doing with forces. I need to give a look at this. Henry? Thanks. So forces push or pull. Probably many of you are familiar with this already. Basically Galileo was the first person that could come up with this idea that, in fact, sort of the natural kind of motion of something is that it just keeps its velocity. So if you don't actually act any force on it, then a particle or some object will keep on moving at constant velocity forever. And he sort of deduced this from a thought experiment, which we basically now know as Newton's first law, but it's really Galileo. And so if there's no net force on an object, then the velocity cannot change. So forces are vector quantities. So if there's more than one force, you add them vectorially. Actually, Newton's laws only really hold in inertial frames. So if you're on a turntable or even on a sphere, then you don't really, you can't expect Newton's laws to exactly hold. Right, and then from daily experience, we know that sort of accelerating objects, something that's heavier, more massive, is harder than something that's lighter. And so this is a kind of formulation of Newton's second law, F equals ma. And so, of course, there's many kinds of, this is the classic kind of problem solving in physics, right? So using Newton's laws to figure out how an object will move is, kind of a whole art form in itself. And so these are kind of various tricks that you should sort of keep in mind when you're solving these problems. So first is to, firstly be clear about, what system you're actually applying Newton's laws to, because actually you could apply it to many different situations. So even in this one, there's maybe 3 ways that you can apply it. And applying it, to different parts of the same system is the kind of standard trick that you will often use to solve these problems. It's also a vector equation, so if you've got forces in 2-dimensional space, then you can treat them separately. Equilibrium is a special case when forces all cancel. And so gravitational force is a typical type of force that we'll be looking at. Weight is actually the magnitude of the force required to prevent a body from falling freely. So weight is actually measured in newtons as opposed to kilograms, as you see on scales. These are 2 balanced scales that, so one is working on different principles. One is basically balancing the gravitational forces. Another one is balancing the gravitational force with the spring force. So this one on the left will work on the moon, while the one on the right will give a different reading. Normal force is the force that originates from basically the molecular deformation. So a rigid object resists trying to have its shape changed. So this means that if you put a block on a table, it's gravity force down, but there's another force upwards which is preventing it from falling down. Friction is another force that we'll look at more in a different chapter, but it's a force to oppose the motion of an object. So if you're trying to slide it, then there'll be a force to resist that. Okay, so I think this is pretty much where we got up to, if I recall correctly. So another type of force that you'll encounter often is tension. So this is another kind of classic problem that you'll be asked to solve. So if you have a rope that's attached to something and then you're pulling on it, then this basically provides a way of transferring the force from, well, originally you to the block. So it's useful just to kind of remember or just to understand where the forces are in a rope like this. So basically you just always, well, the way I do it at least, is to always just draw the arrow that's at the two ends of the rope. And generally the arrows for a rope are always inwards, because obviously if you try to move the ends of the rope together, it will just flop, right? So it's kind of no force. But then if you're pulling it, then there is a force, right? So tension is kind of the force due to this kind of pulling, and there's actually going to be two forces involved: the tension of the rope on the block if it's attached to something like this. So the tension on the rope will provide a force on this block. And we'll do Newton's third law in a second, but there's another force which is in the opposite direction, which is basically the force on the hand due to the rope, because of course when you pull this object, you'll feel that it's kind of resisting the movement, right? And so that's the tension that you're feeling in the rope, which is acting in the opposite direction. So that's the force that's experienced by you by pulling on this block. And so tension always points away from the attached objects. And you see these questions with pulleys in them. And when you first see a pulley question, it looks enormously complicated, but actually it's not so complicated, at least for these types of questions. So generally we don't consider the pulley itself to have any mass, and so in that case the only force, the only role of these pulleys is simply just to change the direction of this force. So it's just a device to have the forces of these two ends of the rope acting in different directions. It's just literally all it does. So it just changes the force vector. Because otherwise, if you have this rope here, obviously you can only have them sort of pointing in opposite directions like this, right? Because you just got the one piece of rope, the rope is always in a line like this, right? But with a pulley, actually you can kind of alter that configuration so that the forces are now not necessarily just exactly opposite to each other, but say one is at a right angle, or maybe any other angle. And so in this configuration, the forces are tension, force due to tension is this way and this way. Now, if it's again this way, again you keep in mind that the rope is like this, and then the arrows are always sort of pointing towards the middle of the rope. You can always sort of remember it like that. Okay, so that's that. Okay, so with that in mind, let's have a try at this question. So the suspended body in this figure here weighs 75 newtons. Is T equal to, greater than, or less than 75 when the body is moving upward? So firstly, at constant speed. So if it's constant speed, what is T going to be? Exactly 75, yes, exactly. So it's constant speed. So by F equals ma, well, yeah. So the acceleration is 0. Constant speed immediately tells you that acceleration has to be 0. And then F equals ma, so acceleration is 0, that means the forces are 0. And if the forces are kind of 0, then basically, well, okay, so the force due to gravity, which is down, has to be cancelled by this tension upwards. Right? So those two forces have to cancel because that's the only way you can make the total force 0. So in order for them to cancel, there has to be exactly 75. Okay, so what about if the body is increasing in speed? So it's moving upward, but it's getting faster upward. Sorry, which one? Gravit, yes. Gravit, because the acceleration is sort of in the upward direction, right? So it's moving upward, but it's increasing in speed upwards, so the acceleration is actually in the upward direction. And if the acceleration is in the upward direction, the force must also be in the upward direction. And then that means that when you have the two forces, there's the force of gravity down. But this tension force is not necessarily the force due to gravity, right? So if you pull on it harder, it will speed up, or if you're kind of not pulling it very strongly, then it will actually slow down. So this tension force will be larger than 75 in the upward direction. Okay, and then the decreasing speed, yeah, this has to be less than. So that's the opposite case. So it's moving upward, but it's decreasing in speed, right? That means it's decelerating. And if it's decelerating, the acceleration is actually down, right? And if the acceleration is down, the force is down, and then if the total force is down, then this force due to gravity, which is pointing down here, is actually going to be greater than the tension force provided here. Okay, so finally we've got Newton's third law. So again, I'm sure you all heard this, but when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So it's a very famous phrase. Now it's so famous that you can sort of stop thinking and not realize exactly what it's saying or the real definition. And so there's a few sort of points that you need to kind of be careful of. Yeah, do I have that on next slide? Right, no. Okay, so the first point that you need to realize is that this is a statement of two objects, right? So it's not just a single object. You can't have Newton's third law actually just with a single object, because this whole thing is talking about two objects, what's happening when two objects are coming together and they're exerting a force on each other, right? So, so there's that, right? So keep it in mind that it's a kind of a two-object kind of relationship. And these Newton's third law, the forces are always acting kind of in, well, the opposite direction, as it says. And the way that I think is clearest to write is, so if you use this kind of notation, so this is the force on the book from the crate, right? So basically there's a force that's experienced by something, and then there's a force provided by something, right? And so a kind of mathematical statement of the third law would be that the force on the book from the crate is the is the negative of the force on the crate from the book, right? So basically there's two parties, one is providing the force to the other, and then it's mutual because the other object is also providing force on the first one, and then they're acting in opposite direction. So if we kind of boil down this more physical real situation to this kind of idealized diagram like this, then the forces would look like this. So some examples. So gravity is an example of where you have Newton's third law. So there's a force on the Earth due to the moon. So maybe we should start with the other ones because that's the more sort of common one to think about. So that gravity acts on the moon and it maintains it in orbit, right? So there's a force on the moon due to the Earth, due to gravity. But there's also a equal and opposite force on the Earth due to the moon. Notice that less because the Earth is so much bigger, right? But nevertheless, it's still there. Another one is the normal force. So, for example, if you've got a table and a ball on it, then the one that you normally kind of always think about is the force on the ball, right? So there's a force upward because the table is being compressed and all that stuff that we were talking about before. So there's a general upward force provided by the table. But of course, from the point of view of the table, there's also force down exerted by the ball. Imagine yourself there underneath the ball. If it was you instead of the table, then you'd feel that force of the ball, provided down on you. Okay, so why don't we go through this together? So let's just draw all the forces that are between these two systems. Between these three systems. And let's kind of keep in mind sort of Newton's third law and make sure everything is following whatever we said. So let me draw this. So I've got the table. All right. So can you shout out all the forces that are acting on this system? And perhaps we should, so this looks like a really simple problem, but you can actually get pretty confused over everything. So let's say the mass of the cantilever is little m, and then this is big M. All right. Okay, so yep.
So you got cantilever on the table on the cantilever.
Hold on. So what you mean due to?
So like the cantilever is exerting force on the table and vice versa.
Right. So I think are you talking about gravitational force or normal force? Or?
Not yet. Well, both, but
yes.
Right now it's just normal.
Okay, normal force. So normal force of table on the cantilever, right? Okay, so that is, so we can call that.
And then vice versa.
And vice versa, yes. So there is the force on, so we should call it force on the cantilever due to the table. And this is force on the table due to the cantilever, right?
And then you also have gravity acting on both of those.
Right, yeah, so we've also got gravitational force, which is going to be, this one's going to be little mg, and we've also got gravitational force, this one will be big mg, right?
And the table and the cantilever also have very small gravitational force.
Right, yeah, on the Earth, there's a gravitational force that's pulling the Earth towards the table, right? That's what you're saying, yeah. That's right. Also, gravitational force of Cantilupe table. Gravitational force from Cantilupe on Earth. Yep. So we can start to sort of, so the way that you said it there is good because we're always working with Newton's third law pairs. So now we can start to look at, all the forces balanced because this whole thing is just sitting there on Earth, nothing's moving, right? So all the forces should actually cancel. So for the Cantilupe, that looks okay because this normal force is going to cancel this force due to gravity, right? What about the table? So we've got two forces on the table there, both pointing down. Probably we need some forces on the table, otherwise the table is going to fall into the center of the Earth. Yep.
You have the normal force of the table.
Yeah. Normal force on the table due to the Earth. Okay. And the Newton's third law pair.
The force of the table against the Earth.
Yeah. So the Earth is feeling a force from the table, actually. Okay. Let's see if we've got them all now. Yep, okay, so I think we've actually got them all now. Alright, so now let's try and match up all the magnitudes of these things. So firstly this FCT, assuming this is all equilibrium, right? So what should that actually be? What number or what expression? Assuming this is mass little m. So this is not moving, right? So we've got that force down, which is mg, which is some number. We can, if I tell you what m is, we know what that is. So then what is this one? Yeah, so mass of small m also times g, right? Yeah, okay. So FCT is also little mg. Then by Newton's third law, these are equal and opposite, right? So this is also little mg. Okay. And then what's this one going to be, actually? FTE.
The sum of small
Right, yeah. So we can view this from the point of view that, okay, well those are, if there's three forces here on the table, then they have to balance. And so here's little mg and big mg down. So this has to be the sum of those two, little mg, big mg. But maybe let's also think of that in terms of, is that kind of reasonable? So say I didn't really know that, say I didn't work it out like that, right? Why do you think it should be little m plus big M G for this one? Is there a kind of a way to think about that? Or why do you think that might make sense, actually?
gravity, the table and the cantilever are 1 unit. So to
Yeah.
account for the entire mass, you have to sum.
Exactly, yeah. So you might think, you might take your system as actually being this kind of whole block here, and you just sort of forget about the fact that there's, the cantilever and the cable, just sort of think of that whole thing as a block. And then, of course, you just look at the mass of that whole block. So then, in order, so the normal force due to combined gravitational force should be the counteract gravitational force, the sum of those things. And so this is mg, this one. So now we should check that all the forces cancel. So yeah, it cancels here. These ones also cancel, and then all the forces on Earth also cancel. So nothing's moving, which, as it should be. Otherwise, this would be some kind of rocket and we'd be moving something. Yeah. Okay, so even for this pretty simple example, there's actually kind of a lot of forces involved. So you got to sort of think it through a bit carefully. Okay. All right. Yeah. Okay. So this is actually kind of the things that I was already mentioning. So, so firstly, the third law always acts on kind of different objects. So whenever we were writing the Newton's third law pair, we were always looking at two different objects. So we started with normal force on the cantilever from the table, and then there was a normal force, the Newton's third law pair of that normal force, which is on the table. And this means that, like this and this one, this is a Newton's third law pair. But, for example, these two acting on the same object, these are actually not really Newton's third law pairs, even though they're opposite in the same magnitude, equal and opposite. That's just a product of this particular situation, that it's an equilibrium situation. So we're in a situation where all these forces are cancelling each other. In fact, if you were told that, maybe say this thing was in an elevator and it was all moving up, actually this normal force would be bigger than the gravitational force, as we've already seen in a couple of examples. So, those don't actually need to be balanced. It's just, for this particular example, they are balanced, but those are not Newton's third law pairs. So, these are Newton's third law pairs, like this one and this one is, and this one and this one is, but not all the pairs are Newton's third law pairs, okay? And yeah, so for this one, as we kind of started off doing, it's actually kind of always useful to write them in pairs. So if you wrote them kind of randomly, you might actually accidentally miss one. So. Okay, so all right, so we've got an elevator situation. So suppose that the cantilever and table of figure 5.11 are in an elevator cab, so it's like this. So, and it begins to accelerate upwards. So do the magnitudes of FTC, and FCT increase, decrease, or stay the same? So, this is almost like what I was just saying, actually. Yeah? So, so if now we're accelerating upwards, what's the size of FCT or FTC going to be? Sorry. Did you have your hand up? No, just pointing at something. Okay.
So
Yeah.
Both of the magnitude are increased, but they're still same.
Both magnitudes are
Same to each other.
same. Right, okay, so I see how you're reading the question. So I think, yeah, so you're saying that they're both the same size, this one, that one, but they're larger than mg. Right, okay, yeah, that's right. Yeah, so they increase because, yeah, so now maybe draw this choice. Don't care about the Earth anymore. And now we're in an elevator. So now this thing here is no longer just mg, and it's gonna increase a bit, yes. And well, maybe we should rub that one up now too. Okay, so if we just look at kind of this subsystem here, and we apply Newton's laws to it, so basically what we'd be saying is that F total is MA, and so FCT plus, minus mg is equal to MA. So we know that this thing is positive, so that means that this thing here must also be positive, meaning that FCT is bigger than mg. Okay, are those two forces still equal in magnitude and opposite direction? Okay, so you already answered that. So yes, they're equal in magnitude, opposite in direction, because they always are. Do the magnitudes of FCE, I think FCE meaning that's actually this one. So I didn't quite follow the notation yet, but CE must be the gravitational force between the cantilever and the Earth. So actually it's just mg. And then the Earth, okay, I rubbed out the Earth, but anyway, so EC is force on the Earth. Does that increase, decrease, or stay the same?
Just stay the same.
Stay the same, yeah. Because this one is just gravity, right? And basically, gravity is always just a constant force. So this force is just always mg, but then the tension force, normal force can change. And yes, they're always equal in magnitude opposite direction because these are Newton's third law pairs. Okay. All right. So, oh yeah.
I don't quite get what FCT minus mg. Why would you do that?
Because so Newton's third law, F equals ma. This is actually talking about the total force on the object. So whenever you use F equals ma, you should really actually you need to add up all the forces on the object. And here, by this dotted box that I drew here, I'm basically saying, all right, so let's consider the system that I'm talking about to be just the cantilever alone. And we know the cantilever's mass, that's little m, so that's fine. Now we need to add up all the forces on the cantilever. So we know that the gravitational force is just down, and here's the normal force from the table to the cantilever. And so there are two forces on this object, and this one is upward. Normal force is, well, in this configuration always up. and mg is down. So basically that's the sum of the two forces. We don't actually know, we know what that one is actually, because it's little m times g. But we actually don't really know what that one is. But we don't really need to know what it is, because in this question it is just asking whether it's going to increase, decrease, or stay the same. And basically at the beginning the acceleration is 0. So this at the beginning, we know that that's equal to 0, and so these are equal to each other. But then it starts to increase. So, and it's increasing, sorry, the acceleration is, what does it say? Begins to accelerate upwards. So the acceleration we know is actually a positive quantity because the acceleration is in the upward direction. So, and then the mass is always positive. So basically this thing has to be some number that's bigger than 0. And so if that's bigger than 0, then we can deduce that FCT is greater than mg. It's a slightly mathematical way of saying it, but basically it just comes down to the fact that there's two forces here. In order for it to accelerate upwards, there has to be a total force upwards, and so this blue one has to be slightly bigger than the black one. Okay, so there's a couple of sample problems. Would it help to do some sample problems? Okay, all right. So let's maybe do one. All right, so figure 5.12 shows a block S. So this one with a mass of 3.3 kilograms. The block is free to move along the horizontal frictionless surface and connected by a cord that wraps over a frictionless pulley. The second block, H, this one here, with a mass of 2.1. Cord and pulley have negligible masses. The hanging block H falls as the sliding block S accelerates to the right. Okay. All right, so we've got basically this situation, and basically the movement of this is just that it's going to like roll down. So this block H will fall down, and then it's going to pull this other block to the right. Find A, the acceleration of block S, the acceleration of block H, and the tension in the cord. Okay. So, I mean, what I normally do with these things is to, even if they give a diagram, I can still redraw the diagram, because when you kind of redraw the diagram, you sort of get everything sort of in your mind. Okay, so this one is big M. This one is little m. Okay. Then, now in these questions, so they've drawn these two forces here. So this is the gravitational force down, and then this is the normal force up. But we can consider this the movement of this block, and just think about what the total movement this one is. And so firstly, well, this is a kind of a two-dimensional example. So there is a sort of an upwards direction and a horizontal direction. So for block S, so in the vertical direction, so we can write the total force is going to be Fn and they say GS, but I mean, we basically already know it's mg. And this thing's going to slide along this table. So what is the acceleration in the vertical direction for this block S? Yeah, just 0, right? Yeah. So it's just going to slide left to right, right? So there is no vertical direction. So the acceleration in the vertical direction is 0. So basically Fn is just always going to be equal to big mg, and that's about it. So in the vertical direction, there's nothing very interesting. So normally I don't even draw it, because in these types of questions, it's if there's a slope or something, it'll be relevant. But this configuration is kind of a classic type of question. So I basically just ignore it. So forget about the vertical direction for this block. Okay. Now we can draw the forces on this one. So there's the tension due to the rope, and according to sort of the rule that I had before, basically the tension of the rope is always acting towards the middle of the rope. So, and they're always the same magnitude. So that's one force for this one, and then this one does have force of gravity on it. Which is in that direction. And then the role of this whole pulley is just simply to kind of change the direction of these of the tension force due to the rope. So it doesn't really do anything more than that. So some people like to draw kind of an equivalent diagram where everything's in kind of flat space, where they just kind of reorient everything so that like this. Some people like to do that. Actually, I think I prefer just to keep it like this, because when you start to modify the physical sort of system, you can maybe make a mistake somewhere. But so some people like to do that. Okay, so we've got all the forces, all the relevant forces, so that, there were some forces here, but they cancelled, so forget about them. Okay, and then let's see, what's the question? So find the acceleration of block S. Okay, so basically what you can now do is to think about what system you're going to apply Newton's laws to. So in principle, you can apply it in Newton's laws in 3 ways. So you could apply it just to this block S. So this was block S, right? Yes, block, the other one called H. So you could apply it to block S, and then you would get basically, so Newton's laws, second law. So block S alone. So for this one, you would just say, okay, so T equals ma. So there's some acceleration of this whole block. It's all going to slide down. That's right. Now you could apply it to block H alone. And then here we've got to add up all the forces. And, well, let's keep the vertical direction as positive. And G is equal to... so in this case, the acceleration will be actually in the negative direction. So we could do it like that. Or we could apply it to actually block S and H together. And in this case, well, yeah. So maybe this is why sometimes people like to draw it in this way. But the total force on the combined system would actually consist of basically these three forces, two tensions on the rope. But actually the tensions of the rope always kind of cancel out. So this doesn't actually provide a movement in terms of the combined system. So this one would be kind of like T minus mg is equal to m plus m, because it's a combined system, big M plus m, A, and then it's kind of down, so we better put a minus sign there. Okay. And because we're not given actually what the tension of the rope is, actually this is the equation that you want to use actually. Because block S, we don't know the acceleration, that's what we're trying to work out. Tension, we're not given. So kind of like, well, we can't solve that equation, can't really solve that equation either. But this one we can solve because we are given the masses of the two objects, and so you just have to rearrange this for A, so it's going to be mg over big M plus m. So that's acceleration. Put some numbers in if you like. Acceleration of block H is actually the same because this is like one kind of rigid object. So this is also the acceleration of block H. Well, yes, yeah. So the acceleration of the whole system. So block S, block H, block S and H. And then finally, to find the tension in the cord, we can use one of these other equations. Put that into here. So the tension would just be big M G over M plus M. I didn't put numbers in, but I think you can do that. Okay, that's fine. All right, okay, so we'll leave it there, and today's Tuesday, right? Yes, okay. Your homeworks are due today, right? Okay, so just put your homeworks here, and we'll continue on Thursday.